So today we're going to learn about lattice energy, and lattice energy is the energy required to completely separate 1 mole of a solid ionic compound into gaseous ions. And we only talk about lattice energy for ionic compounds. Here's an equation for lattice energy. You don't know what any of these things mean, so I'm going to tell you. Q plus is the charge of the positive ion. Q minus is the charge of the negative ion. R is the distance between the ions. You could think of it as a radius, although it's not a radius because it's the distance between the two ions. K is a proportionality constant. You're not going to have to worry about knowing what that K is. We don't ever calculate lattice energy. We just look at, we compare whether one ionic compound or another ionic compound would have a larger lattice energy. So let's do some problems. And we always want to think about this equation right here when we are doing problems. Which compound has a larger lattice energy and why? So first we're going to look at MgF2 versus calcium, CaF2, calcium fluoride versus magnesium fluoride. Well, the first thing you want to check are the charges. And both compounds have fluorine, so we don't need to worry about the fluorine charge. So we check the calcium and the magnesium. And you look at your periodic table, magnesium is in the +2 column, calcium's in the +2 column. This isn't getting us very far at all now, is it? The charges aren't different. And the only thing sorry about that. The only thing we can look at is either charge, Q plus, Q minus, or R, the radius. It's the radius of a whole ionic compound, and the distance between the two nuclei would be half the distance of the entire ionic compound. So that's what we're going to check now is R, sort of the radius. Again, both compounds have fluoride, so there wouldn't be any difference in the size of the fluoride ions. So now we're going to look at the calcium and the magnesium ions, the cations. And this is getting back to the previous chapter about number of shells. When we're checking the sizes of ions, we check how many shells each ion has. Okay, this might be a little bit confusing to you. The magnesium ion, it has 2 shells of electrons. You might read that and go, wait a minute, magnesium's got 3 shells of electrons. That is true. But remember, when we have the ionic compound, Mg has a +2 charge. So we've taken away 2 electrons from magnesium. By the way, you might want to pull out your periodic table at this point, because without the periodic table, you cannot count your shells of electrons. Okay. So magnesium itself is in the 3rd row of the periodic table, and magnesium has 3 shells, but we take off the outer 2 electrons and we're only left with 2 shells of electrons. So now let's check calcium. Find calcium on your periodic table, and you'll find calcium has 4 shells of electrons, but in an ionic compound like calcium fluoride, calcium has a +2 charge, so that outer 4th shell is lost. So the calcium ion has only 3 shells of electrons. So which of these is bigger, 2 shells or 3 shells? That's right, 2 shells is smaller and 3 shells is bigger. So since the calcium ion has more shells of electrons, the R for CaF2, calcium fluoride, is larger than the R for magnesium fluoride. Okay, this last little therefore piece gets some people confused. So let's just remember the charges were the same. So the charges for calcium fluoride and magnesium fluoride are the same, but the radius is in the denominator. Oops. Okay, so the radius for fluoride in both of them would be the same, but calcium is bigger than magnesium. If calcium's bigger than magnesium, then calcium fluoride has a bigger R. You'd be dividing by a bigger number, which means calcium fluoride has a smaller overall, lattice energy. Eek. There we go. And magnesium fluoride has a larger lattice energy. Okay. Next page. Actually, where did that go? So let's do another problem. This time magnesium fluoride versus magnesium oxide. We're going to check the charges first again, so get out your handy dandy periodic table, look up your charges. They both have magnesium. Both compounds have magnesium, so the Q plus is the same. The fluoride is a -1. We ignore that there's 2 fluorides here, by the way. We're just looking at the charge of a single fluoride ion. So F, -1. O, -2. So we already see oxygen has a bigger charge than fluoride. And based on our lattice energy equation, since oxygen has a bigger Q minus than fluoride's Q minus, MgO will have a bigger lattice energy than MgF2. And there we go. Okay, lithium fluoride versus lithium oxide. We checked the charges. Both of these have lithium, so what are we going to check? Hopefully you got it. We're going to check fluorine and oxygen, which we just checked right over here. Look at that. Fluoride -1, oxygen -2. Do you know the answer? Here it is. Lithium oxide has a larger lattice energy. Okay, next one. If you want to try this on your own, go ahead and pause. Check your charges, then check your shells. Which one has a larger number of shells for the positive or negative ions? Which one has a bigger or smaller charge for the positive and negative ions? And I'm about to show you the answers. So charges are the same. That doesn't help us out. We have to check the shells. And here we go. Lithium has got, well, lithium ion has only 1 shell of electrons. Sodium ion has 2 shells of electrons. Sodium ion is bigger, has a larger, so sodium fluoride has a larger R. And recall, R is in the denominator, so we're dividing by a bigger number, which means sodium fluoride has a smaller lattice energy. And lithium fluoride has a larger lattice energy. Again, because R for the equation for lattice energy is in the denominator. Moving on, molecular polarity. So we learned a few classes ago about how a bond can be polar, nonpolar, or ionic. So we can be polar covalent, nonpolar covalent, or ionic. For our polar bonds, we can add up what are called bond dipoles to find out if molecules are polar. So to determine if a molecule is polar, you add the bond dipole vectors in the molecule. Don't worry, I'm going to teach you how to do this. You do not need to write down. You will learn how to do this in a moment. Okay. Again, I'm going to teach you how to add the bond dipole vectors. Don't worry about that. But when adding those bond dipole vectors, that should say if. That does say if. I was getting myself confused there. If, when adding the bond dipole vectors, you start and end at the same place, we would say the bond dipole vectors add up or sum to 0, and therefore the molecule is non-polar. So if the bond dipole vectors start and end at the same place, when you add them, the molecule is non-polar. If they start and end when you add them, if the ending point and the starting point are different, we say the molecule is polar. What is this vector addition stuff? What am I talking about? So we're going to do some problems. We're going to find out if the following molecules are polar or nonpolar, and I've given you some information about the order in which we should do the steps. So first you need to have your Lewis structure and the molecular geometry. We've already done the Lewis structure several times for SO3, and it is trigonal planar, so I'm just going to put that up there. Okay, so I've put up the Lewis structure, and this molecule will be trigonal planar. When you put in your bond dipole vectors, you want to check oxygen is more electronegative than sulfur over here. And because of that, we put the bond dipole vectors pointing toward the oxygens. You don't need to put the delta plus and delta minus in there yet. All right, now notice I've redrawn, actually duplicated, the 3 bond vectors. And now you're going to learn how to add up the vectors. We're going to, whoa, that's not what we're going to do. we're going to add the vectors. We've already done the Lewis structure. We got the molecular geometry. We drew the bond dipole vectors on the correctly drawn molecular geometry. Now we're going to add the vectors. Adding the vectors, you connect heads of the vectors to the tail that you're going to add to the vector that you started with. So here we go. I'm going to start with green. So here's my green vector. No, I didn't want to separate those out. And now I'm going to take my purple vector and I'm going to add it to my green vector. I connect the tail of my vector that I'm adding. See that right here? Connect the tail of the vector that you're adding. Connect it to the head of the vector to which you are adding it. So I'm putting the tail of this vector onto the head of the last vector. Okay? And now I'm going to add the red vector. I have to put the tail of the red vector to the head of the purple vector. Okay, there we go. Now, are we starting and ending at the same place? Well, if you look very carefully, it looks like there's a little bit of space here, but we're going to ignore that little space. We pretty much started and ended almost exactly at the same place. It's hard to get exact amount, exactly at the beginning and the ending because of how we draw things, but basically we started and ended at the same place here. So let's look at what we were given. Let's see, where were we? If you start and end at the same place, the bond dipole vector sum to 0 and the molecule is non-polar. So we would say the molecule is non-polar. We have a non-polar molecule. So we just learned SO3 is non-polar. Now we're going to do another one. All right, so first you draw the Lewis structure, done right here. Right there, there you have it, Lewis structure. Then you draw your, oh, that doesn't look so pretty. Then you draw your structure in the correct geometry. So because SO2 has, because SO2 has 2 bonded atoms and 1 lone pair, steric number is 3. So steric number 3, 1 lone pair, we have a bent structure, this structure right here that you see. And I've duplicated the bond arrows. The bond dipole vectors point to the oxygen because it's more electronegative. Then I have to add up the bond dipole vectors. Let's look at our instructions again. They're quite messy. Whoops. Okay, so we did our Lewis structure, we did our molecular geometry, we drew the bond dipoles on the correctly drawn molecular geometry. Now we have to add up the vectors. And to do that, we connect head of the vector to the tail you're adding to the vector. So here's the vector. We're going to connect the tail of this vector to the head of that vector. There we go. Do you notice that the start and the end point are totally different places? Totally different. They're nowhere near each other. In this example right here, the start and end point were very, very close. In this example, the start and the end point, totally different spots. You see that? We started right here, right there. Oops. Started there. We ended there. Very different places. And our instructions tell us, our instructions say that if when you add the bond dipole vectors, you start and end at different places, the molecule is polar. So, did we start and end at different places? Yes. And therefore, this molecule is polar. Now, what you need to do when you have a polar molecule is you're going to draw the overall bond dipole moment onto the structure. And the overall moment, you start where you started. So let me we'll use black. You start where you started. We started about here. I'm just moving this over to the right a little bit so that you don't see it on top of the vector addition. And we end about here. So start where you started, end where you ended. And where you end, you draw your head. Where you start, you draw your tail. And you take that piece squeeze, and you move it directly on top of the original molecule. Okay, and that shows you the overall polarity of the molecule that you're working on. So it shows you your delta plus and your delta minus for the molecule, not for the bond, but for the molecule. So again, you start where you started, you end where you ended, draw your overall dipole moment. That's called a dipole moment. Okay, we're going to do 2 more problems, and if you want to pause this and do these on your own, go ahead. I've sort of already shown you the CO2, but I haven't added the bond dipole vectors yet. So Lewis structure first, then your geometry, then add your vectors, and then make your conclusions. Draw in your overall dipole moment if you need to. Okay, so CO2, here's my vectors. Start with 1. This is kind of weird when you add them together. I have to put my tail where my head was, so it actually lands right on top of the other one. And then the question about, did you start and end at the same place? Well, I started right here, and note I ended right there. So I started and ended at the same place, so that sums up to 0. Therefore, the molecule is non-polar. And I do not put in any overall dipole moment. Okay, SF4. All right, SF4, we've got our Lewis structure right here. We've got our correct geometry for the molecule. It should be a seesaw. And I've drawn the seesaw structure with the dipole moments for each bond, the bond dipole vectors pointing toward the fluorines because the fluorines are more electronegative. And then I have the 4 vectors over on the right side, and I need to add them up. This is not adding them up here. Oops, hold on, I've got to group those real quick. Okay, so I have to put tails to heads. So let's see, this one will go there. It doesn't matter what order you do this in, you get the same result no matter what. I'm just connecting heads to tails. Notice we do not end where we started. And if we end in a place different from where we started, we say the molecule is polar. And I have to write the overall final dipole moment. And you should see, I started on the right side, I ended on the left side, so I'm going to draw an arrow. Where you end, you draw your tail, just like the ending point had the tail, the head. The ending point had the head, the starting point had the tail. And I take that vector and I put it, oh dear. Try that over again. I take that vector and I put it right on my original molecule directly through the original central atom. And I show my delta plus and my delta minus. And there you have it. So the next thing that we're going to work on, learn about, are double and triple bonds and something called a sigma and a pi bond. It's very easy. Single bonds are always sigma bonds. Every single bond is a sigma. And it's just a name. It's just a name for a bond. A double bond has a sigma and a pi bond. So anytime you see a double bond, 2 bonds, one of them is a sigma, one's a pi. Anytime you see a triple bond, you have 1 sigma, 2 pi's. So we're going to do some problems. We're going to count sigma and pi bonds on these molecules. So single bonds are sigma, so I'm going to circle all the single bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9 sigmas so far. We don't want to forget that. That symbol I just wrote, that is a Greek small s, which is called sigma. That's a sigma. Okay, double bonds have 1 sigma and 1 pi. I have 3 doubles, 1, 2, 3. So I have 3 more sigmas and 3 pi's, because double bonds count as 1 sigma and 1 pi. So this whole thing has 12 sigmas, 3 pi's total. Okay, you can pause and do this other one on your own and then forward and you'll see the answer. So I'm going to just go put little sigmas here. 1, 2, 3, 4, 5, 6, 7, 8, 9. one of the doubles is a sigma, one is a pi. It doesn't matter which one you mark as a sigma or a pi, it's just about counting them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sigma, 1 pi. Very easy, right? Okay, a couple more for you to do just to get the practice of counting. So just one more. Count your sigmas and pi's. Again, pause it if you want to wait. Sigma, sigma. Go ahead and pause if you don't want, if you want to do this on your own. Sigma, sigma, sigma. Now triple bonds count as 1 sigma and 2 pi's. So I have 1, 2, 3, 4, 5, 6 sigma and 2 pi bonds in that structure. Very easy and straightforward. Okay, last thing for today is hybridization of atomic orbitals. This is also another thing that's extremely easy. You just have to sort of pay some attention. It's very easy, straightforward. The key is that s, p, and d orbitals, we learned about these in the last couple of chapters ago, the last test we had, or quiz. So s, p, and d orbitals, they can come together to form what we call hybrid orbitals. Hybrids are when you take two different things and they come together and they make something new. Like a mule is a hybrid of a donkey and a horse, I think. Something like that. So hybridize just means you're taking two things that are different, putting them together to make something new. And all of this information here, just some background. An SP would just mean an S and a P come together. SP2, these superscripts tell you how many of each orbital. So 2 P's and 1 S come together to make SP2 hybrids. And the number of hybrids you make would be how you just add up these superscripts, and that's how many hybrid orbitals there are. So 2 plus 1 is 3 hybrid orbitals. So here you have 3 plus 1 makes 4 hybrid orbitals. 3 plus 1 plus 1 makes 5 hybrid orbitals. And the last one we add up to 6. Okay, if you're trying to figure out what your hybrid orbitals are, all you need to do is find out what your steric number is. Your steric number tells you your hybridization, and that's what you must memorize. It hopefully is quite easy, but steric number 1, oh, hold on a second. When I was filling out that chart, I was thinking I had a problem there. Okay, here we go. Steric number 2 means you have SP hybridization. The superscripts on the hybridization add up to your steric number. So if you have steric number 2, we always have an S, and then we have however many P's we need to add up to this 2. So steric number 3, we have 1 S. 1 plus 2 is 3. Steric number 4, 1 S plus 3, 1 plus 3 equals 4. Now all of a sudden we get to steric number 5. Remember, there's only 3 p orbitals in an entire shell. We don't have, it's not possible to have 4 p orbitals in a shell, so we couldn't have sp4. So s then p3 adds up to 4, but we need 5 total orbitals, so we need a d. So 1 plus 3 plus 1 is 5. Steric number 6, we start with 1s. We add 3 p's, gives us 4, and we need to get all the way to 6, so we need 2 more. Now, everything I just said, if you want to write some notes down, however it makes sense to you to, you don't want to memorize this, that steric number 2 is sp, 3 is sp2. You want to use that idea that the steric number is how many orbitals you need, and you always start with an s. You add p's until you get to your steric number. If your steric number is more than 4, well, sp3, we can only go up to 3 with the p's. So now we need to add on a d if you have steric number 5. And if you have steric number 6, 1s plus 3 p's plus 2 d's is 6. Okay. Now over on the right side here, I've given you an idea of, oops, I just crossed that out. Again, over on the right, you have an idea of what does this mean, these hybrids. So I'm taking 1 s orbital and 1 p orbital, and I'm putting them together. I'm getting 2 orbitals. So however many orbitals you start with, that's how many you end up with. I have 2 orbitals, And notice they have this great big side and then this little teeny tiny lobe. They have a big lobe and a little lobe. So I start out with an S and a P, 2 orbitals, and I end up with 2 orbitals. And this picture over here is just showing you the nucleus is right here. Here's my nucleus, N. And the orbitals surround themselves around the nucleus. The little lobes are actually hidden. You can only see the large lobes because the little part of the lobes would be inside the other lobe, the large lobe of the other hybrid orbital. And then down at the bottom, I'm just showing you an sp3. We start with 1 s, 2 p orbitals. So we have 3 total orbitals. And we end up with 3 total orbitals. Each one has a large lobe and a little lobe, just like the SPs. When you get these hybrids, you get a big lobe and a little lobe. And then on the very last picture over here on the right, we're showing you if this was a nucleus, right in the middle there, this is how the 3 lobes would line up around the nucleus. These are our 3 hybrid orbitals. You can't see the small lobes because they're hidden inside of the big lobes. And it would form this triangle in a plane. Whenever you have trigonoplanar electron geometry, it's because you have steric number 3 and you have this picture. Last thing. And that's it for today.